So I guess a few quick announcements. Obviously, there is kind of a mini reading week next week, so Wednesday's class won't be canceled. I guess we'll still have Tuesday and Friday's lectures as normal. I'd like to finish up the AVL unit on Tuesday is the goal, and because your midterm 2 is on the following Tuesday, and I think that's where we can just do the cutoff there. And the labs for that week, because there are labs that fall under the reading break weeks, reading break days will be canceled. So we'll just kind of push those labs back 1 week. We might actually push back the labs another week. I'm just seeing how the labs are gonna, the final 3 labs are gonna line up with the material we have left. So we'll see. They'll certainly be canceled next week, and we're gonna have no labs for one of the other weeks because there's always just 10 labs. You shouldn't need to resize anything in assignment 4. I mean, you can if you want, but you shouldn't have to with how it's set up. So yeah, there's a question: are we responsible for resizing in assignment 4? I mean, you always have to resize. You'll have to create new nodes for the tree, but after that, once you allocate space for your heap, you should allocate enough space that it never fills up. If you don't want the assignment due on reading week, I can have it due earlier, but that's just how it is. It's either Riley's asking why the assignment is due on a holiday. Again, it can be due earlier, but it can't be due later because otherwise you're just not going to get any feedback before the midterm. So if you don't want to hand it in on a holiday, just hand it in before. Yeah. No, there won't be, Josh. Any other questions? Yeah, so I can't really extend that assignment just because it does take us time to grade them, and I want to make sure we give you feedback on something that's testable before the actual exam. Because you are, like, trees and heaps are going to be 2 of the topics on the next exam, and I just want to make sure that if there are kind of major conceptual misunderstandings there, that we identify on the assignment, that you can get that feedback in time. Any other questions? How did the quiz go today? Have you guys, I'm assuming you probably haven't seen rotations in binary search trees before. Oh, a few of you have. Did you do it in like in 115 or 116, or just in stuff outside of the prerequisite courses? Okay, cool. Okay, transfer students, previous program. Okay. Yeah, I've noticed that since I'm teaching 115 and 225 right now, that there seems to be a lot of overlap. I'm not sure why. I mean, I guess in some ways it's good to see things multiple times to solidify your understanding. But I am wondering why there is as much overlap as there is with other courses. It might just be because, again, typically courses kind of have owners within the department, and they're responsible for kind of updating things as the kind of North American curriculum changes occur. And it might just be that they both kind of used to be separate, but as they're adding new things to the curriculum, they're both kind of adding similar things, and there's a lot of crossover. But that's certainly something I'm going to talk about, because I don't think, I don't see any time in the previous, at least recorded kind of instructors. I can go back to where there's someone that's actually taught both courses. So it might just be that there is a little bit of a disconnect there. So last day, we didn't quite finish the worksheet. So maybe we'll jump onto that and we'll try to move through that fairly fast and then go to the new stuff, the AVL stuff. So on the binary search tree worksheet, I think we finished the binary search, but we didn't quite finish, I guess, really just this chart up here. So we can finish that off because, again, I do think it's worthwhile to spend some time talking about the runtime of the different things we've kind of talked about, again, at a faster pace than 115, but again, still, it is somewhat of a review. So we finished this binary search where the idea with the binary search is we're always going to kind of start in the middle. And if we're looking for like the number, I don't know, 72, then we're going to know, okay, I don't have to search anywhere on this side. So now the new range of my array is going to be from here to here. And I'm going to go into the middle of that range and say, okay, which side is 72 on? Okay, it's on the right side. So this is going to be my new range. So I can cut off all of this half. Now I can go to the middle of that and I can say which half of it is it on? Okay, it's in this range, so I can cut off that whole half. So the idea with the binary search is that every time you're cutting off half of the search space, the area of the list or collection or whatever it is you're working with, that you're searching for an item in. So I guess the main thing this shows us is that when we're finding an item in a sorted array, we can do that in just log n time. What about if it was a sorted list? So again, this is supposed to just be a linked list here. Can we also get a log n time in a linked list? If we're doing the find? What do we think? No, because the thing with arrays is because we can directly access the middle element and look at what that value is and compare it with the item we're searching for, it allows us to access this item right away. And then we can just say, okay, the high range of my array is here and the low range of my array is going to stay the same. But with a linked list, we actually can't access that middle element right away. We're actually going to need to start at the head and go like next, 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 if we want to do something similar to a binary search. So instead, what we're probably going to have to do is say, okay, I'm looking for some value. Maybe I can see if it's closer to the front or the back, but you're still going to have to just go next, 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 next. So it's going to be O of n, because as the input size grows, the number of next you're going to have to do is going to scale at asymptotically the same rate. So I guess, again, I want to move this kind of fast. So again, traversing, it doesn't matter if it's a to traverse any of these data structures, again, to visit all n items, that's just going to be O of n. Again, we can do this in multiple ways with the binary search tree, whether it's balanced or not. Again, if you think about the level order, again, we're just going to put all the items into a queue, and it doesn't actually matter. We're still going to visit all n elements. Similarly, in an array and a linked list, again, to visit all the elements and print them out or something like that, it's just going to be a loop that goes from the head to the tail or the front to the back. So in terms of finding in a binary search tree, the average case here is supposed to be similar to this array down here, where, again, we can start at the root, and if we're looking for, again, 72 or something like that, we can say, okay, I know that 72 is to the right, so I don't even have to look in the left side at all. And then we can just go here and we can say, okay, 72 to the left or the right? Oh, it's to the right again, so I can get rid of this whole side, which is 72. Okay, 72 is here, and I found it. But again, on this time, I could have got rid of that whole side. So similar to the binary search in an array, the structure of a binary tree is kind of doing the same thing, where the the root of the particular subtree we're searching for is the middle value, or roughly the middle value in that range. And then from there, we can kind of say, okay, I don't need to look in the left subtree, I don't need to look in the right subtree, based on which direction we know to go to locate that value we're searching for. So in the average case, a binary search tree is log n. But what about the worst case? What is the worst case we can have with a binary search tree? Yeah, I guess it's the height, which, and I guess that height could be n if we've got a binary search tree like this, right? Where it's essentially just a linked list. So the idea here is that with just a binary search tree, and again, this one we haven't seen AVL trees, there's a difference between the average case when things are kind of roughly on either side versus the worst case when it is essentially just a linked list. What about insertion? So I guess we can just go across these last two columns. Insertion into a binary search tree. Again, we know that we're always going to, and maybe kind of going on what David's saying, we know we're always going to insert onto a leaf node. So we're always going to be, no matter if it's the worst case or the best case, it's always going to be based on the height. Because again, we always insert into a left node. We go left, right, left, right, left, right, left, right until we get to a null. We say, okay, this is the right place to insert a new node. Similarly for delete, again, it's roughly going to be based on the height. Because to find the node, the worst case we can go is find at the very bottom, it's a leaf node. But even if it's something more internal in the tree, like if it's the root, which we can find right away, even if we remove the root, we know that we're going to have to we're going to have to replace it with something like its predecessor. So that actually might require traversal all the way to the bottom of the tree. So we'll say that I'll just put heights here for basically just to show that almost all these operations, I guess even this is technically O of height as well, really depend on the height, except for the traversal. The traversal is the only one that we're always just going to visit all n of the elements. What about for a sorted array, a sorted list using an array? How quickly can we insert into that? So yn squared. So we've already got I mean, we can look at this array down here. We've already got a sorted array. If you had to just insert one number in here, what's the quickest you could do it? Yeah, and keep it sorted. So I'm saying n squared and log n and an n. So I think the issue is with the log n case, Owen, I think, again, you're right that we could figure out where to insert it in O of n, in O of log n. But the problem is if we want to insert something here, what we're going to have to do is we're going to have to shuffle every other item back. So even if we can find it really quickly, we're still going to have to possibly rotate or shuffle, I guess, all of the elements past that point forward. So I think really it's going to come down to O of n, because again, what we can do is, again, even if we find it in log n, then the shuffling is going to take n. Whereas again, if we start and just do a normal loop through the array and say, is this what I want to insert? Is this what I want to insert? Is this what I want to insert? Oh, I found the place I want to insert it. Okay, put it here, and then shuffle, 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 shuffle. So it'll just be one loop that has to go through all n elements. Yeah, so you're right that you can find it in quicker than n, in quicker than n, but the shuffling is going to be the bottleneck there. What about for a linked list where we don't have to do any of the shuffling? Yeah, so again, the linked list, the problem is even to find the item we saw was O of n. So again, we don't have to do any shuffling, but just to find the place to insert it is going to take O of n time. Similarly, with a deletion on the array, we can find out where to delete it in log n, but then to do the shuffling back to fill in that gap is going to take up to n. Whereas again, just to find the item to delete it is going to take O of n in the linked list. So I guess what I wanted to take from this chart here is that one of the motivating factors to use a tree over linked lists in an array is that we are hoping to do better on most of these common operations, being able to insert or remove items from this collection and find them. And I guess, obviously, if you want to print out all the items in the collection, it's always going to be the same. But I think the problem is we see here that the main difference here is that where these are in insertions where the lists are n and our deletions are n, the binary search tree is height. So again, the issue here is that when a tree is balanced, the height is log n, but if it's not, then the height is just O of n. So if a BST is not balanced, what we see is we're actually not getting any improvement in any of these areas. It's just going to be the same thing, O of n. And again, in some ways, the tree structure is actually more complicated to actually look at and maybe visualize sometimes than just a linear list, which we're so familiar with using. So the main idea that I wanted to kind of get through before we get into the AVL trees is how really keeping a tree balanced is really where we get all of those benefits we're trying to get in terms of efficiency with a tree implementation over a list. And again, we get those if we can make sure that tree is going to stay balanced, so the height is bound by log n. Does that make sense? Okay, so we're going to probably have to spend today and next day on doing some of our AVL rotations. But what I'll do is I'll open up the AVL worksheet. As you'll see, it's quite big. I think it's got 4 pages, 1, 2, 3, 4. Yeah, because we're going to do a bunch of removals and focus on kind of some larger trees where we have to do multiple rotations. But I'm hoping to kind of at least get maybe a page and a half-ish done today. So I'm going to zoom in a bit. Zoom in again. So from the videos, we saw that the balance factor of a node is defined as the height of that. Oh, let me get my pen out again. Is the height of the node's left subtree minus the height of its right subtree. And a tree is balanced if all nodes I guess let me the balance factor of each node is between -1 and 1. Or I guess we could also just say the balance of a node, the absolute value of it, is less than or equal to 1. So all we want is we want to make sure every single node in the tree is the difference between its height of its left and right subtrees is at most 1. And we talked about in an AVL tree, and when we do a rotation, which is what we're going to do to maintain this balance, when we do an insertion or removal that creates an imbalance, is again we want to make sure we're still a binary tree. We want to make sure we're still a binary search tree. And we want to make sure that the AVL tree still is balanced. So there's a binary tree property. I guess I could write the property. There's a binary tree property, which just is that all nodes have at most 2 children. There's a binary search tree property, which is respect to how items are ordered. So again, all nodes in the left subtree have a key less than the current node's value. All nodes in the right subtree have a value greater than the current node's value. And the balance property is what we just stated above, where all nodes also, the difference in the heights of their left and right subtrees is at most 1. So the plan for rotation is, again, typically when we do an insertion or removal, again, we're going to insert again at the bottom of the tree. And what we're going to do is we're going to go progress up from where that insertion occurred and keep checking all the way up to the root if there's any imbalance. Similarly, for a deletion, again, if we delete like a leaf node, we're going to go up from that point. If we delete a node with a single child, we're going to attach attach the single child and go up from that point to check for an imbalance. If we delete an internal node with 2 children, again, we're going to replace it with one of the with his successor or predecessor, which are going to be much lower in the tree. So from that point, we're going to go up from there and see if we've created an imbalance. So the general idea is that we are going to first identify the lowest place with an imbalance. Or like, I guess, deepest from the root, if we're thinking about depth. Identify the deepest node with an imbalance. So again, kind of we're going to go up from the insertion or removal. And then what we're going to do is, I guess, when we find that imbalance, we're going to rotate to correct the imbalance and which restores the 3 properties above. So I mean, obviously, if we're using tree nodes that only have a left and right child, we can't add. We're never going to have a third child. But again, sometimes when you're drawing it out, when we have kind of bigger trees that are more well connected, then as opposed to just inserting a new, just working with the simple example we'll start with, we do have to kind of connect again the subtree somewhat. And in the videos, I kind of talked about how the original parent of the imbalance inherits one of the subtrees from the child that's rotating up to be the new parent. And so again, in that case, it is kind of important to think about the binary tree property in the sense that we can't have a third child. Obviously, the binary search tree property, the rotation, how and where we make our rotation affects the order of the elements. We just want to make sure that all of the nodes in the node's left subtree are smaller than the key, and all the nodes in the right tree are greater. And then the balance again is just what we're doing the rotation to fix. We figured out that we've got I guess a deeper or a subtree that's got a larger height, and we're rotating that up so it balances out with the subtree that has a smaller height. So what we'll do is I wanted to kind of show off all of the different rotations in the simple form before we actually work at a large example, because it's important that we understand the 4 different rotations that can occur before we can kind of identify and fix these in larger trees that have many more nodes. So I think I showed these off in the slides, but again, I showed that there was 3 different ways we could arrange 3 different nodes, 5, 7, and 8, in a way that's imbalanced. And the first here is that when we insert the 5, what we see is that there's an imbalance on node 8. And the imbalance occurs when we go left and left. So, and again, maybe I should also say that this could actually be, this isn't necessarily the root, there could be other nodes connecting to this above. What we see is that node 8 has a left imbalance. We go left and then left from the node that's imbalanced and down to where that newly inserted node caused this imbalance. So what that means is what we're going to do on this node is we're going to, I guess I can kind of draw a circle here, and we're going to rotate it right. And what that's going to get us is, again, if I draw this circle again, and we rotate these nodes, the 8's going to kind of rotate off the edge, the 7's going to rotate to the top, and the 5's going to rotate up just a little bit. And whatever was originally connected to the 8 is now connected to the 7. Does this make sense? Cool. So the next one, which is similar, is going to be if we have an 8, then a 5, then a 7. And here, again, the 8 is out of balance, but we go left, then right from that imbalance node to reach the place that caused the imbalance. So in this case, we're actually going to have to make 2 different rotations. What we're going to do is first rotate left here, and then we're going to do that a second rotation. So maybe I'll do them separately. Maybe I'll just say that eventually we are then going to need to do a second rotation here, and we'll see why in a second. So when we make that first rotation, rotate left, what we get is we get that oh, that should not be an 8. That should be a 5. We just rotated around this, and what we got was that we just, again, rotated the 7 up to the top and the 5 over the other side. And now, really, we're back in the first case up here. Now, what we've got is just this issue up here, where now we've got a left imbalance on 8. So what we're going to do is now rotate it again. Similar to what we did at the top, which is again just going to get us that final rotation where we've got the 5 and the 7 and the 8. Any questions so far? Okay, so the last two cases are really just mirrors of the first two, where again, I could have the exact opposite as the first one, where I've got like a 5, then a 7, then an 8. And again, now in this case, the 5 is out of order, and we go right from the 5. And so again, what I'm going to do there is I'm going to rotate left on that 5. Which, as we might expect, is just going to put the 5 over the top. The 7 is going to rotate up to the top, and the 8 is just going to kind of rotate up a little bit. And the last one is kind of the mirror of the second one. So we've got a 5, then an 8, then a 7. Again, we've got an imbalance on the 5. We go right and then left for that imbalance. And what that means is we're going to first rotate left here. Then after, we're going to have to rotate right on the whole thing. And again, what we probably notice is that now this, after the first rotation, we're back in the third case, meaning that we're going to have to do, I didn't leave myself enough space there. Yep, I clearly just didn't even look at my arrow there. There we go. Which is going to, again, just get us back to the original 7, 8, 5. Any questions about this? No questions? So let's take, yeah, so let's take a second to look at a case here. So why I've got some trees here is because, again, I did it with just 3 nodes before, but the slightly more complicated case is when we've got other nodes. We know that everything in purple is going to be between 1 and 30. We know everything in orange is just going to be greater than 80. So if we do a rotate left here, we know that we're going to have 30 up at the top. We're going to have 80 over here. And we're going to have the above 80 below it. We're also going to have now 1 to the left of 30. But now that 30's left is pointing to 1, where it used to point to this purple here, again, that's the problem where, that's the binary problem where we can't actually, 30 just took on a new left child, the 1, but it already had a left child there. So yeah, so you're right. What we did is we did a rotation. We did do a rotation here. But the only place that the purple can go to is, it has to be between 30 and 1. So it's going to be to the right side of 1, which is gonna balance this tree. But again, we know that these values have to be right from 30 and, or sorry, right from 1 and left from 30. Oh no. So right from 1, left from 30, left from 30, right from 1. So that works. So how are we actually going to do this in terms of code? Let's say this is the node we want to do the rotation on, n. N's the node that we've identified as imbalanced. So what we probably want to do is set some temp pointer to point to, so again, a temp pointer to point to n's right. So now what we want to do is we know that we want to connect N. We kind of want to make this connection here. We want to update N's pointer so that it now points to temps left. So we've effectively done this. This was kind of step one. This was step two. Now all we need to do is set temp to point to N. So that is doing this thing right here. And I guess what we do is we'd call this on some node above. So originally 1 was pointed to by some node above it on the tree, but this is the first place we found the imbalance. Now we just want to say that the root of this whole subtree here, root of this whole subtree is no longer 1, it's now going to be 30. So I guess we should return the fact that 30 is now the root of the tree. So I'll say that we're going to return temp as the new root. And that's kind of this step up here. We haven't this time, and that's why we were just returning. I mean, I guess we could have said set, if we had a parent in our node, we would have just said set temp's parent to n's parent, and n's parent would have been temp. But we don't actually, because we're going to call this, we want to know what the new root of this subtree is. Just so, because again, whenever we do a traversal, we start from the root. So we wouldn't want we wouldn't want to still think that this is the root of this tree because it's no longer the root anymore, if that makes sense. Oops, shouldn't have done that. So if we think about how to actually do this in code, we'll see that the code actually for this rotation actually isn't that bad. So all we have to do here is a few lines, but again, nothing too bad. So we can say, let's make a tree node. I don't know, temp. Maybe I might do this in one smaller font. Then so that's step one, that's step two. Step three, and step four. So the rotation actually isn't very difficult. It's not difficult at all. It's just kind of thinking about this. And again, obviously rotate right's the exact opposite. We're going to say tree node temp equals n left, that n left equal to temp right. and temp right equals n, and then return that temp. And all we're going to do in the second more complicated cases, which are again the ones that we have to do that temporary rotate before getting back to the original case. Again, what we might have noticed is this rotate right then left here is we do one thing and then we're back in the first case. So we're going to take advantage of that by just saying that we're going to say that we're going to say n right. So we want to rotate right on it. We're going to rotate right on the right subtree. Then we're going to rotate left on the node. So what we're doing here is we're saying, okay, let's rotate right on my child, which is right here. We're rotating right on that child, and we're saying, make my right arrow point to the new root of that, which we saw is gonna return this 7. So after this operation's done, our tree is gonna look like this. And then we just call the rotate left, because that is just a rotate left problem now. Does that make sense? There's no recursion here. Where are you seeing a recursive call? That's not a recursive call. This method's called rotate right left. It's calling a rotate right, which would be the exact opposite of this. Yeah, so that's just going to rotate right on the child, which is going to get us, which is what we're doing. I've got in this red circle here, which I can circle a different color. So we're saying just do a normal rotate right on the child, which we've seen is what it's going to do is it's going to set up all those things, and it's going to return the new parent, which is the 7. So now what we've done is we've said 5's new right child is going to be that 7. And now I'm just in the original case that we kind of solved up here, which is just a normal rotate left. That's why we return the node at the end. So again, when we rotate around a subtree, when we call it from the one above it, it sets its child pointer accordingly to that new root of that subtree that's been rotated up. Does that make sense?